Hi, and welcome back. This is one of 3 lectures on Chapter 3 of your book, which deals with the basics of motion. Now, the plan for the semester is to start simple and then add on detail until we can get more complex. And part of starting simple means that we need to make a few assumptions. So, the assumptions that we're going to make right now is that the motion that we're looking at, that we're trying to model, is along one direction. Now that direction could be the x direction, it could be the y direction, it really doesn't matter, but it's going to be along one direction. Also, the things that we're looking at, we're going to assume are basically just little points with labels. So we're going to ignore any sort of internal structure that they have. Now that said, in order to talk about motion, we need to define a few concepts. And the first one we're going to start with is a point. So if you think about a point in space, no matter what your perspective is, no matter what your viewing point is, whether it's here, 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 it could even be from, the other side of the screen as you watch this video, that point physically in space does not change. So its location is where it's at. But it really doesn't do us a whole lot of good in physics to just draw a little dot and call it a point without referencing it somehow to a coordinate system. When we do that, what that does is to allow us to link that whole idea of theory to empiricism via math. So that's what we're going to do. So let's draw a coordinate system. We'll do it like this. Like that. Now I'm going to call this y. I'm going to call this x right here. That's the x-axis. Here's the origin. And this right here, this position in space, I'm just going to call x1. Now, notice that it doesn't really matter where I draw this coordinate system at on this sheet. That point's location is still the same in space. So the nice thing about that is that we can draw our coordinate systems wherever we want. And in doing so, that means that we can potentially pick a place where it makes our math easy. It allows life to get a lot easier than it could be if we pick a poor position. So that's the goal. So we have a point in space, and the reference is here at the origin. Now, points by themselves are of limited use, at least right now. So what I'd like to do next is to define a big concept called displacement. Now, so in order to understand displacement, what I'd like you to do is to think of the following scenario. So imagine that you are in your house. We'll say it's right here. There's a house. I'm going to locate the position of your house here. We'll call it x1. And then out in the driveway or in the parking lot or wherever, you've got a car. So here's your car right there. And I'm going to denote the position of the car as x2. Now, so if you look here, relative to the origin of our coordinate system, this right here, this distance right here, is the length of x1. Likewise, if you look here, this distance right here, this would be the length of x2. Okay. Now, if I were to walk from my house to the car, the distance that I would cover would be this distance right here. So if I wanted this distance right here, what I would do would be to take the length x2 and subtract away x1. So I have this, I subtract this piece right here off, and that leaves me with this distance right here. Now this is a calculation that we do in our head all the time, but obviously not on a sheet of paper. Now this right here is defined as the displacement, delta x. Now we know from mathematics that delta means change in. So really what this is your change in position. Okay, so that's your displacement. So this right here, x2 minus x1 is displacement. Now, displacement, firstly, is along a straight line. Now, it also consists of a distance, and what we're about to discover, also a direction. Now, distances are lengths, and things that have magnitudes and directions are vectors. So, what we have here is our first example of a vector. So, to get a better understanding of what's going on, let's work a few examples. I want you to imagine playing a little bit of golf. So, I'm not a huge golfer, but this is a good example. So here is our coordinate system, right here. This is y, this is x. Now, imagine you have a golf ball right here, and then here's the hole we want to try to put this golf ball into. So our golf ball is at x1, which is 5 feet away from the origin. Now, the hole we want to put this thing into, we'll say is x2, 20 feet away from the origin. What I'd like to do is to find the displacement here. So we know, we have been given, that the position of the golf ball is 5 feet away from the origin, and the position of the hole is 20 feet. We would like to find the displacement. Now, the equation for displacement, at least right now, is x2 minus x1. Where you end up minus where you start at. Okay, that's conceptually how I want you to think of it. So, delta x is x2 minus x1. That's 20 feet minus 5 feet, which is 15 feet. Now, what I'd like to point out here is that the ball has to travel 15 feet this way. Now, if you think about the number line and the x-axis, this is in the direction of positive numbers. So keep that in the back of your head as we do the next example. So, in this example, and let me label our axes, I'd like you to think of having a store right here that you're going to go into, and you park your car over here in the parking lot over here. Now, so here's your car, here's the store, and from a location standpoint, this is where we're going to start, 100 meters away from the origin. The store sits 75 meters away from the origin, and it's where we're going to end up. Now look at how I index these things. 2 is where you end up, and 1 is where you start. Now we're going to reindex this in a moment, but I just wanted to point out this is the way I want you, again, to be thinking about these things. So here we know x1 is 100 meters, x2 is 75 meters. We would like to find the displacement. So again, the displacement is where you end up minus where you started. Here, 75 meters minus 100 meters. And when you do the subtraction, you get minus 25 meters. Now, the way to interpret this is that to get to the store, you had to walk 25 meters, but in the minus x direction. So, this is the direction that you walk towards the negative numbers, and as a consequence, there's a minus sign out in front. So as we can see, displacements have magnitudes. That is how far you walked, and also directions. And in one dimension, the direction is denoted by being positive or negative, being in the positive direction or in the negative direction of the numbers. Now, that said, we're going to reindex this. One way you can at least initially think about this, we're going to reindex it again, just to remind us, is that it's where you end up minus where you started. Now, the little 0 here is typically called a naught. It means nothing. Or 0. So, what we're going to do to eventually reindex this to, and I'm not going to do it yet because I want to be sort of consistent with the notation in your book, is we're going to say that this is going to be our position when our watch reads 0. So just sort of keep that in the back of your head as something that eventually we're going to do. But what I like to do again is just to show you some of the caveats of the displacement, because displacement isn't the same thing as distance traveled. Displacement is the straight line distance and direction between 2 points in space. Okay? So, to make this sort of clear to us, let's think of another example. And the example is going to be this one right here. Let's pretend that you get a little bit of free time and you can go out and enjoy yourself, and you're going to go to a lake. So here's the y-axis, here's the x-axis. You know, maybe you park your car right here. Here's your car. This right here is 15 meters. I'm going to call this x sub c for where your car is. That's your car's position. And then maybe over here, this right here is the lake. All right. Now I'm going to call this x sub l for lake. And maybe it's 50 meters away from the origin. Now what I'd like to do is to walk from the car to the lake, and then walk back to the car from the lake. So for journey 1, and I'll just call this 1 and this 2. For journey 1, we start at the car and we end at the lake. So where you end up minus where you started. We start at the car and end up at the lake. That's 50 meters minus 15 meters, which is 35. Now, the next leg of our journey has us walking from the lake to the car. XF minus X naught. Where you end up minus where you started. You end up at the car. You started at the lake. So your total displacement is what you get when you add up all of the displacements as vectors. It's just simple vector addition, like what we covered last chapter. Delta x1 plus delta x2, which in this case is 35 meters plus minus 35 meters, which is 0. So I think it's pretty clear that we did go somewhere. We walked to the lake, had some fun, and then walked back to the car. But from a displacement standpoint, we started at the car and we ended at the car, which means that overall we didn't go anywhere. So as you can see, displacement isn't a total distance. It is a straight line distance from where you start and where you end up. Okay. Now, there is a way that you can use displacement to sort of get the correct distance here. Instead of looking at adding together the vectors, all you do is you add together the magnitudes. So the magnitude of the total displacement would be the magnitude of x1 plus the magnitude of x2. Now magnitude means that positive value, the lengths. So that would be 35 meters plus 35, which is 70 meters total. And that makes sense. Now, the next thing I'd like to talk about is the next big concept. So far we've covered displacement, but that's nowhere near enough to even begin talking about physics. So the next thing I want to talk about is something called velocity. So velocity is sort of like a speed plus a direction. Now, we're going to talk about a couple different types, but the first one I'd like to talk about is something called average velocity. Now, it's a vector. As you can see, it has a direction to it. And I want to stress, it is an average. We'll get to that here in a second. So the way it's defined is the following. Average velocity is defined as your displacement over the time. Now, you'll notice here that you've got a delta t here. It works conceptually the same thing, or the same way rather, as delta x. Just to remind you, delta x is where you end up minus where you started. Delta t looks like what your watch reads whenever you end up wherever you do, minus what your watch read when you started. So if I were to expand this out, it would look like your final position minus your initial position over your final time minus your initial time. So the best way to get a handle on what velocity is like is to work some examples. So what I'd like you to think about is the motorcycle. So here's a problem. We have a motorcycle. So example. Starts at the origin and accelerates to a final position of 1,500 meters. The elapsed time is 30 seconds. I would like to find the average velocity. So, I'm going to draw a coordinate system. So the first thing you do when you solve a physics problem is to draw a picture. That is, after you've read the problem a few times. Let's label our coordinates, y and x. Now, here's my motorcycle right here. Its initial position, according to the problem, is at the origin. It's going to go this way, we'll say. So this is going to be the direction that it travels, ending up somewhere down here in a final position, at least when we see it, of 1,500 meters. So it's going to up here. Now, the final time we're going to say is 30 seconds. It's an elapsed time. And we're going to pretend that we started with a stopwatch, so our initial time was 0. So here, I have been given the following information. My starting point is at 0. My watch starts at 0. My final position is 1,500 meters, and my watch, when I hit that position, reads 30 seconds. I would like to find the average velocity. So, we know from our discussion earlier that the average velocity is your displacement over the elapsed time. Where you end up minus where you started over what your watch says when you end up there minus what your watch said when it started. XF, 1,500 meters. X naught is the origin at 0. TF is 30 seconds, and your watch started with 0. Here, your average velocity is going to be 1,500 divided by 30, or 50 meters per second. Now, you'll notice that this is positive. What that means is that when your motorcycle hits here, it is traveling to the right in the direction of positive numbers. Because remember, velocity is a vector. Now let's work another example. So in this example, what I'd like to think about is a situation where you have pulled up to your house, maybe in your driveway or whatever, and it's raining. In fact, it's raining here right now as I do this lecture. Now, here's Y, here's X. Here's your house, we'll say. Right there. We'll say that your house is, I don't know, 30 meters away from the origin. And we'll say that you parked your car over here. $50 meters away from the origin. You open up the door of your car and you sprint. And it takes you, I don't know, about 8 seconds to get into the front door of your house. So what I'd like to do is to find your average velocity. We have been given an initial position of 50 meters, a watch that starts at 0, a final position of 30 meters, and a watch that reads 8 seconds when we run through the door. And we'd like to find our average velocity. So look what I've done here. I've drawn a picture. I've labeled my picture with the information that I've been given. I know I'm trying to find this, so I write down the things that I've been given. I write down what I'm trying to find, and then I ask myself, what equations do I know of that exist, that we've talked about, that would allow me to solve this? And the only one that we really know of right now is this one right here. So once again, if you expand this out, and you plug in what we know, you solve for it, you end up with somewhere around minus 2.5 meters per second. Now, if we're consistent about our significant figures, there's one here, and one here, which means that this is about minus 3 meters per second. And what I'd like to point out here is the negative sign. The negative sign means that when you run, you're running this way. So here you are, trying not to get soaked, going that way. And it makes sense. You're running in the negative direction, and as drawn, your house is in the negative direction relative to the car. So what I'd like to do now is to look at the graphical interpretation of average velocity, because I think it helps a little bit. So let's draw something here. This is probably something that everybody here can get. You've probably done it yourself. So here is a number line right here, and then there's another one right here. It's going to be a long one. I'm going to label these, but the labels on these axes are going to be a little different. I'm going to call this X and this T. Now, what we're going to do is to walk from our car to the house. If this is the 0 on the x-axis, I'm going to call our car somewhere around here. This is where our car is, right there. It's at minus 20 meters. So this right here, I'm going to say is where our car is. Now, up over here, this is where our house is. So here's your house. It's at 30 meters. Okay. So let me draw our little graph here, and then we'll talk about what's going on. Okay, so think of progressing this way. All right, you're walking forward in time, but you're walking along the x-axis. All right. So you walk from your car to the house initially. So step one, here's our initial position. We'll call this x naught. From here to the first position right here, your car, or your house rather, at 30 meters. We're going to hang around in the house for a while, and then we're going to, oh, I don't know, leave the house and go to the car. So here we are. We start at 30 meters. We start walking towards the car, and then we get, oh, I don't know, 10 meters away from the origin. And what we do is we realize that we forgot our keys. So you slap around in your pockets for a little while looking for your keys, and you realize, oh man, I left my keys, I think, at the house. So we're going to leave from here, and we're going to go back to the house. Open the front door, reach around the side, and grab the keys to your car. We're going to walk from there, and we're going to go back to the car. Okay, so how long did this take? Well, we're going to assume that our watch starts right here when we start walking from the car to the house. So our initial time here, at the beginning at least, is 0. Then when we get here, oh, I don't know, maybe it took 60 seconds for us to walk here. So 60 seconds passed for us to get there. We're going to hang around in the house for a while, almost an hour. So here, when I go to leave the house, 3,600 seconds has elapsed. Just a touch less than an hour if you take into account the walk time to the house. Now, over here, we're going to start walking to the car. When we get to, like I said, about 10 meters away from the origin is when we say, oh man, I think I left the keys at the house. Here at T3, it's 20 seconds. 20 seconds into the future, past leaving the house. Ah man, I got to turn around, got to walk back, slapping around in your pocket, trying to find your keys. So T4 is when you finally realize you left your keys there. It's 3680 seconds. You finally get back to the house. Didn't take you too long. You get your keys and then you head out at 3720. And you finally get back to your car at 3780 seconds. So let's see what's going on throughout this entire curve. The first thing I'd like to point out here is that even though I started at minus 20 along the x direction, as I walk forward in time, I'm walking also up towards the positive numbers. So I expect when I actually find out what my velocity is here between the car and the house, the average one at least, I expect it to be positive because I'm walking this way. So the walk from the car to the house, we'll call that the average velocity from 0 to 1. It's just v1, we'll call it. That's delta x1 over delta t, 1. So that right there is going to be x1 minus x0 divided by t1 minus t0. Where did I end up? At 30 meters. Where did I start? 20 meters, minus 20 meters rather. What did my watch here say? 60 seconds is what it read when I got to the house, and it started at 0. So when I do this right here, you see it's minus and minus 20 is positive. This is going to be 50 meters over 60 seconds. And if you do the math here, it ends up being about 0.8 meters per second. So we're going to hang around in the house for a while. So chilling at the house, chilling at the house. We'll call that the average velocity 2. Delta x2 over delta t, 2. X2 minus x1 over t2 minus t1. Okay, x2 is 30 meters, x1 is, 30 meters minus 30 meters. I started there, ended up there. I didn't go anywhere, right? Let's just go ahead and plug the times in to be consistent here. This is the 3,600 seconds minus 60 seconds. So we hung around at the house, 59 minutes. But when you do the math here, you get 0. So, like I had mentioned before, you're chilling at the house. You're not doing anything. You're not going anywhere. Your displacement for that part, journey 2, we'll call it, is nothing. So if it helps us, we'll label this as 1, 2, 3, 4, 5, 6, and then 7 going back. All right, so this is 1, this is 2. So let's do 3. So 3 has us leaving the house to go to the car and then realizing that we left the keys, or we don't have the keys, or we need to find the keys. So walking back to the car. Again, average velocity for part 3. Delta x3 over delta t3. X3 minus x2 divided by t3 minus t2. So what's x3? It's 10 meters before we actually get to the origin. What's x2? That's 30 meters. What's t3? T3 is 3620 seconds. And what's t2? Well, that's, remember when we left the house, 3600 seconds. So 10 minus 30 is minus 20. 3620 minus 3600 is 20. Minus 1 meter per second. The minus is negative, and take a look. For this part, we're going this way now. So at the beginning, we went this way, which gave us a positive velocity. And then we chill at the house, nothing. And now we're going back towards the car in the negative x direction. Okay? So, makes sense. 4. That has us patting our pockets and looking for the keys, maybe in our jacket, trying to figure out what's going on. Where's the keys, man? So part 4, average velocity of 4, is delta x4 over delta t4. Delta x4 is x4 minus x3. Delta t4 is t4 minus t3. If you plug the numbers in, that's going to be, where's my keys? I'm standing here looking for my keys. I'm not going anywhere. What did my watch read? Let's see. 3680 is when I decided to turn around and head back to the house, but I just started slapping around in my pockets at 3620. So, panicking, trying to find the keys for about a minute. Okay, didn't go anywhere. Okay, now we need to turn around and go back. So here we are, heading back to the house. Path 5. Delta x5 over delta t5. x5 minus x4 over t5 minus t4. Okay, so for that one, we end up at the house. We started 10 meters away from the origin. When we got back to the house, 3,700 seconds had elapsed, starting at 3680. So, once again, 20 meters over 20 seconds. 1 meter per second. But look, now it's positive. And that's because for this leg of the journey, we're going this way. We're going back towards the house, which is the positive x direction. Almost done. Part 6. Part 6 is when we go inside and hunt for the keys, which probably are hanging by the door. So, part 6, delta x6 over delta t6. Once again, so here 30 meters minus 30 meters divided by 3720 minus 3,700. So it took us about 20 seconds to find the keys, but look, we didn't go anywhere when we were doing it. Now I'm going to go up over here just to get a little bit of free working area and keep this all on the same page. And we're going to do part 7. For part 7, we want to find the average velocity of finally actually walking from the house to the car. That's going to be delta x7 over delta t7. x7 minus x6 divided by t7 minus t6. What's x7? Well, I mean, that's where we end up. That's minus 20 meters. Minus. Starting at the house at 30 meters. Divided by, we got to the car at 3780 seconds, and we left the house at 3720 seconds. So, at the top you can see it's a minus minus. It's a minus minus a positive. That's going to be minus 50 meters divided by, the difference between these is 60 seconds, minus 0.8 meters per second. So, looking at all this stuff right here, and then looking back on our graph right here, we can kind of get a sense of what's going on. You can think of the velocity as being present when you have a slope that's not zero. And in fact, that's how you interpret the velocity here. The velocity is the slope of these lines. Here, going from here to here, the slope is 0.8 meters per second. Here, this has no slope, and sure enough, look what happened. This has a negative slope, and if you were to actually draw this out and keep correct scale along t, which isn't really possible here because we'd have to have at least 3,720 squares going this way drawn to scale. But as you can see here, this is a negative slope, this is a zero slope, this is a positive slope, this is a zero slope, and this again is a negative slope. So velocity, it turns out, is the slope of a line when you plot position versus time. That's the way you graphically interpret it. So what I'd like to talk about now is something called instantaneous velocity. Now, average velocity is useful in some regards, but the thing that's really useful in physics is being able to ask the question, what's the velocity of something in any given time? See, instantaneous, or rather, average velocity has got some issues. If you were to say, for example, look here, where you're walking from your car back to your house, one of the issues that you would notice is that you may have averaged about 3 meters per second to the left, but there may have been times in which you sped up, when you slowed down when you were walking, when you sped up, when you slowed down. So at any given time here, your actual velocity, your velocity at that instant, was probably not 3 meters per second. But on average, it was between those 2 points in space. So the bit of information that we're missing is the ability to ask, what's my velocity here? What's my velocity here? What's my velocity here? What's my velocity now? So in order to address that, what I'd like to do is to draw from a little bit of pre-calc or calculus, depending upon where you're at in calc right now. And I'd like to think of a curve that shows us velocity as a function of time, but this curve is not going to be nice and straight and flat like the other ones were. If you remember the one that we just looked at here, we have all these nice jagged discontinuities where it's going up and then now it's flat and what have you. The curve that I want to look at is going to look something like this. Maybe it starts off like that and slows down and like that. So here we'll call this our position as a function of time. Now, so in order to get our velocity, we'll say at this particular position right here, I'd like to know what's my velocity right here. In order to get that, what I'd like to do is to zoom in to this particular location in space and take a look and see what the curve looks like. So if I zoom in here and just sort of blow it up, I end up with something that looks a little bit like, kind of like that. Now, maybe here is the point that I'm interested in. This is where I'd like to find my v of t. I'd like to zoom in even closer. Maybe we'll zoom in there. Let me take that zoom over here. So here I'm zooming in. Looks maybe something like this. Here's the point that I'm interested in right here. This is the velocity that I'd like to find right there. Let's zoom in even closer. Let's just keep zooming in, man. Just zoom, 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 as they say. Eventually, if you keep zooming in, you're going to end up with something that looks like a straight line. And maybe right here, this right here might be where you want to find your velocity as a function of time. Okay, so we'd like to find it there. So here's the game we're going to play. So let me sort of take this and put it off over here to the side and blow it up, so I can work with it a little bit better. So here maybe is my curve, and maybe right here is the point I'd like to find my velocity as a function of time at. But to be clear, from an axis standpoint, I've got position going up and down, and I've got time going side to side. Okay, so what I'd like to do is to play a game. This right here, I'm going to call x as a function of t. Okay, now I'm going to look forward just a tiny, tiny, tiny instant in time right here. This is going to be just a small little tiny itty bitty smidget of time in front. We'll call it delta t. So from here to here in terms of time, that's delta t. From here to here in terms of position, that's delta x. So our average velocity between these 2 points would be, again, delta x over delta t, or our final position is just a little bit into the future. Our initial position was there. And this is our elapsed time. Now, to get the instantaneous time, what I'm going to do, or instantaneous velocity rather, is take the limit as delta t goes to 0 of x of t plus delta t minus x of t divided by delta t. Now, for those of you that are right around derivatives in calculus, or you've had Calc 1 before, you'll recognize this as the derivative of position as a function of time. Okay, and that is the definition of instantaneous velocity. It is how your position changes at a given instant in time. Right there. This right here is the one that's the most important really in physics when it comes to velocities. Now, that said, what I'd like to do now is a quick example. We're going to come back to instantaneous velocity and things like that, but the way the sequence typically works is that most people, when they're taking university physics, are also taking calculus 1 at the same time. And because of that, you might just be getting to derivatives, and you don't have enough of a foundation in derivatives yet to be able to exploit them all as much as we'd like to be able to. So I'm going to do a quick, simple example, and then we're going to spend a lot of time talking about what happens when you deal with constant things. It's going to make our life easy, and then we'll come back and we'll revisit instantaneous velocity and other instantaneous quantities later on. So that said, here's the example I'd like to work. And this is the derivative rule that I'd like to take a look at. It goes something like this. If you have, let's pretend x of t looks like this, t to the n. When you take the derivative of t to the n with respect to t, the n comes down and t loses one exponent up there. So this is the derivative rule that we're looking at. Okay? So I want you to imagine, just for the sake of argument, a position that looks something like this. 4.9 meters per second squared times t squared. Now, were you to plot this, it'd look a little bit like this. It's going to be a parabola. We're going to start at 0. T is equal to 0. It's going to be a parabola that looks something like that. Okay, so here's x of t. So our instantaneous velocity is going to be this: the derivative of position with respect to time, d by dt of 4.9 meters per second squared, t squared. Now, the rules of calculus place derivatives as linear operators. What that means is that if you have a constant sitting out in front of a variable in here, you can pull the constant out. So this right here would be 4.9 meters per second squared. And what we're trying to take the derivative of is t squared. Now, if you look at this rule right here for derivatives, when you take this derivative, the 2 comes down and t loses 1 power in exponent. So this is the same thing as 2 times t. So 4.9 meters per second squared times 2 times t. And if you carry the 2 through, this becomes 9.8 meters per second squared times t. Okay, so our velocity in this particular case, as a function of time, would look like 9.8 meters per second squared times t. So for example, if you look here, you'll notice that I start off at the origin, and the slope of my curve, if you think about what a parabola looks like, the slope at the origin is 0. Well, if you think of velocity as slope, then at the origin, your velocity is 0, which means I'm starting from rest. As I go on and on and on, I go faster and faster and faster. And oh, I don't know. Why don't we take a look and see what what our velocity looks like 5 seconds into the future? So v at 5 seconds is what you get when you take and put 5 seconds here with t. So you do the math. And let me get my calculator here. $49. So 49 meters per second. And if you want to be consistent with significant digits, 1 sig fig here, which means that this would be about 50 meters per second. Okay. But the important thing to see here is that now you can ask the question, what is my velocity at any given time at all? So this is an instantaneous velocity. Okay. Now, we'll come back, like I said, to those later on. So the next thing I'd like to talk about just briefly is something called average and instantaneous speed. Typically, we may cover things like average speed before we start talking about velocity. But here, they're making a big deal about instantaneous speed as well. And so I think it's a pretty good idea to cover this stuff after all that, after our discussion about velocity, which we just had. So speed's very easy to get. Speed, which we usually define just as s, is how far you go over how long it takes. Now, speed is not velocity. And to illustrate that point, let's think about living here in Florida. So let's just sort of sketch the tool that is Florida here. Here looks something like this. So this is a Florida. Looks kind of like that. So I want you to imagine, just for the sake of argument, that Orlando is somewhere like here. Here's Orlando. And Miami, we'll say, is about here. Now, if you were to drive your car from Orlando to Miami, you might take the following path. You get on the car, and it says drive down I-4, hop on 95. 95 sort of takes a little bit of a meandering path here along the coastline, and you end up here in Miami. Now, this right here would be how far you go. But contrast that with displacement. Displacement only depends upon where you start and where you end up. So this right here, this would be the path that you would take according to displacement. And the reason why I want to point that out is because this right here is what concepts like velocity and instantaneous velocity, that is average rather, that's what these things are based on, is this straight line distance. Average being the where you end up minus where you start type stuff, and instantaneous being what you get when you take the derivative of a curve zoomed in so closely that it looks like a straight line. So as you can see, how far you go is going to be equal to or greater than whatever the displacement's length is. Okay, so speed truly is, a physical average. It's, how far you go over how long it takes. Now, I want to be clear, this definition of speed is average speed. Now, instantaneous speed, on the other hand, has a more physical definition. By physical, I mean it's based off of straight up physics definition. So here, if you know what your velocity is, and you get rid of any sign that might be there, this would be instantaneous speed. So instantaneous speed and instantaneous velocity are the same, with the exception of the fact that you've just eliminated the sign, so you're just looking at the magnitude of it. Now, we're not going to really do any examples dealing with that right now. They're not super critical to university physics. I might give you a homework problem or two dealing with them, but nothing that is all that relevant. Okay, so the very last concept that I want to get into here is going to be acceleration. Now, so acceleration is a little complicated to visualize. So you can visualize position very easily if you look at something you are looking at its position. If you think about velocity, if you throw something through the air, your eyes are designed to track the path of that thing over time as it flies through the air. So, from an evolutionary standpoint, we're incredibly wired to see things like positions and velocities. Acceleration is not so much. And I'm going to come to a pretty easy way to visualize it. But before I do that, let's go ahead and define it first. So just like velocity, there is an average acceleration and there is an instantaneous acceleration. We'll start with the average. The average acceleration, this is average acceleration, is how your velocity changes over time. Okay. So just like position, just like velocity is a vector. So let's just do one or two examples of it so you can get a feel for it. And so I want you to think of a motorcycle. So here's the origin. Whoop. Oh, I thought I took that off. So here's the origin right there. No wonder the Y and the X looked a little funny. And maybe here's my motorcycle right here. So a motorcycle, initially at rest, accelerates to 65 meters per second in 8.1 seconds. What is its acceleration? Now, we have been given, and we're trying to find stuff, but we have been given that our initial velocity is 0. Now, I'm going to have us move to the right. This is going to be the direction of our velocity at the end of the day. So here, at some position in the future, we have our motorcycle. It is moving this way with a final velocity of 65 meters per second. Now my watch, because I'm going to use a stopwatch, read 0 when I started off. But when I get to this position in space, it's going to read 8.1 seconds. given. Initial velocity is 0. Initial time, 0. Final velocity, 65 meters per second. Elapsed time, 8.1 seconds. And I would like to find the average acceleration. Now, as you probably saw over here, the average acceleration is just your final velocity minus your initial velocity over your final time minus your initial time. So here, when you write this out, 65 meters per second minus 0 divided by 8.1 seconds minus 0. And when you do the math, you end up with 8.02 meters per second over seconds. Now, if you round this to the sig figs, because I see 2 here, I see 2 here, this ends up being about 8.0 meters per second per second. Now, the way to think about this is similar to how you can think about velocity. With velocity, every second that goes by here, you go minus 3 meters. Here, every second that went by here, you went 50 meters. 50 meters per every second. So, here, the way to think about it is, every second that goes by, your velocity changes by 8.0 meters per second. You start off at rest. 1 second into your journey, you are traveling at 8.0 meters per second. 2 seconds in, and now you're at 16. 3 seconds in, and now you're at 24. 4 seconds in, 32. And so on, and so on, and so on. Now, to simplify the way this has been written, we typically write it as 8.0 meters per second squared. But always think of it like this. Every second that goes by, this is how it changes. And if you do that, it'll be a little bit easier. Now, like I said, the hard thing to visualize here about acceleration is, let me rephrase that. The reason why it's so hard to visualize is because we're not really wired to see it. So the way I want you to think about it for right now is, what direction would I have to push this motorcycle in order to get it to go the way I want it to? So this motorcycle is traveling this way, at least the way it's been drawn, and the problem is accelerating from rest, and it's going to be traveling to the right at the end of the day. So this here, according to my problem, would be the direction my acceleration would be. And what I like to point out is that it's positive. Remember, acceleration is a vector. So that means here the acceleration is in the positive x direction, and the way we visualize it checks out. So what I'd like to do is to work one more problem dealing with this. And I want you to think of a car now. So, you've got a car, and let's have our car travel initially. So the initial velocity is not going to be 0. So we have a car initially traveling at, I don't know, 80 miles per hour. Comes to rest in 6 seconds. What I'd like to know is, what acceleration did the car experience in this time on So here's my car right here. We'll have it start at the origin just to make my life easy. And its initial velocity we'll have be to the right. It's 80 miles per hour. Now we're going to need to convert that to meters per second in order to make this work. So you hit the brakes, and somewhere over here, we don't really know yet. We'll be able to predict that here pretty soon. Our final velocity is 0. Okay. Now, how long did it take for me to stop? Well, I'm going to make the same sort of assumption that I did before, that I'm using a stopwatch. My initial time is 0, and my final time is 6 seconds. So if your car is moving to the right and you want to slow it down, wouldn't you need to push on the car this way to get it to slow down? Well, let's see if that's going to end up being the direction of our acceleration. So, given, find, what have we been given? My initial velocity is 80 miles per hour. I'm going to need to convert that, like I said, and I'm going to leave a gap down here to where I can convert it. My initial time is 0. My final velocity, I actually come to rest. And it takes me 6 seconds for that to happen. Now I'm going to convert 80 miles per hour to meters per second, and the way I want to do that is just doing a direct conversion. 80 miles per hour, I know that there is 0.447 meters per second for every 1 mile per hour. And if you actually do that conversion, you end up with about 35.76 meters per second. Now, you don't round this. Remember, we round at the end of the day. If you remember watching the first video I did for chapter 1, when I talked about, actually I think maybe it was the second video I did, when I talked about significant digits and rounding and what I expect. Remember, the goal is to look at all the significant digits that you have going in and round to the least number at the very end when you're done with your calculations. So we're not going to round this at all. So what am I trying to find here? I'd like to find my average acceleration. So average acceleration, that's how your velocity changes with respect to time. Vf minus V naught over Tf minus T naught. And if I plug stuff in here, my final velocity, you see I'm at rest. My initial velocity is 35.76 meters per second. My final time is 6 seconds, and my watch read 0 at the beginning. And if you do the math here, you end up with somewhere around 5.96 meters per second per second. If you look here, 1 sig fig, 1 sig fig, this rounds up to minus 6 meters per second squared. And look, there's a minus sign. Remember at the very beginning when we were drawing our picture and we were trying to figure out what the direction of the acceleration would be? Well, you would have to push to the left to slow the car down to rest. That's the negative direction, and sure enough, we ended up with a negative. So when it comes to visualizing the directions of accelerations, the question I want you to ask yourself is, what direction would you have to push it in order for it to do what you would like it to do? Now, so simple example. All right, so now we're rounding up to the very, 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 very last topic. We're not going to spend, like I said, a whole lot of time on this, much like we didn't spend a whole lot of time on the equivalent version for velocity. And this is an instantaneous acceleration. So I want you to think of instantaneous acceleration here as being defined in a similar way as instantaneous velocity was. Remember, what we did really to get away from our average velocity to instantaneous was to promote these deltas to differentials. So if your average acceleration looks like this, what I'm going to do is to promote the changes, the change ins, to differentials. And sure enough, this right here is the definition of the instantaneous acceleration. Okay, that's what it is. Now, just a quick, simple example that I'd like to draw from using a problem that we worked before. If you remember before, we had tried to find velocity as a function of time, that is instantaneous velocity. And we ended up with something that looked like 9.8 meters per second squared times t. That was this problem right here. Okay. So what I'd like to do is to find out what the acceleration here is. And again, I want to remind you of the following derivative rule. If you take the derivative of t to the n with respect to t, that is n times t to the n minus 1. So here, if you take the derivative of velocity with respect to time to try to find the acceleration, you're taking the derivative with respect to time of this. The constant right here comes out just like before. Remember, this is a linear operator, which means that you can pull that out easily. And you're stuck taking the derivative of time with respect to t. And if you do that, that's 1 times t to the 1 minus 1, which is 0. T to the 0 is 1. Or you can just note the fact that dt over dt is 1 because it's an algebra object, which means that you have 9.8 meters per second squared. So in that particular problem, the acceleration that that our thing was experiencing right here was in fact 9.8 meters per second squared. That's what the acceleration was right there. Okay, so this concludes lecture 1 of 3 for chapter 3. The next 2 lectures are going to cover lots and lots and lots and lots and lots of problems using constant acceleration. Because remember, like I said at the beginning of this lecture, we want to start with the simplest view, and then we're going to sort of slather on the additional detail as we get better and better, so we can add to the complexity, as opposed to just starting off with something that is so complex that we can't solve it because we don't have the background for it. All right, so next up, dealing with constant accelerations, and then we'll go from there.